All right. So we're going to go over load calculations 26301. So let's look in our books here. Catch up here in a second. All right. Now this one here, Trenton, you have your textbook? It's at the house. Do this. Let's grab a textbook real quick, right? So you can look over it. All right, so going through the PowerPoint here, we'll calculate branch circuit loads. Let's see. Put this in here somewhere. There we go. So anyway, calculate branch circuit loads, apply derating factors, calculate branch circuit ampacity. So this is essentially a continuation of 26, what was it, 26, 110, 111, 26, 111. And where we take, essentially we just take and we identify the loads, the demand that the building or facility that you're actually wanting to occupy, whether it's a home, a business, or whatever, and actually use it for whatever the purpose is. So, so we do a load calculation to determine what the load demand is on that. Let's see. I'm betting my clipper is going to be in my carry bag, but I'll figure that out later. Did you ever get locked in? Still connect. All right.
I can do it on my phone.
Nope, it's fine. We'll share for now until that happens. Or you, well, I'd rather you not, but. All right, so what is the basic purpose of branch circuit load calculation? We just talked about it, right? The purpose is we have a building. It's what are you doing inside the building? If you're just doing office work, well, it's going to be minimum load, right? You got to have heat and air. Okay, it gets cold, it gets hot. And then you got to have lights. Yep. And then you got to have power to run your outlets. Okay, so now what if it was a bakery, like a donut shop?
Ovens, fryers.
Mixers, deep fryers, right? So you'd have to have multiple things. Now a lot of those cookers and stuff are gas. So, but some of them still have electronic controls on, so they still require. Yep. So they require a different amount of power. So what we have to do is we have to determine what the actual power consumption is, and then build a load calculation from it. Okay. All right. So it's to determine the size of the circuit, overcurrent protection, and branch circuit conductors used by the NEC. Now, you remember, memory now, this is memory. If I wanted to determine what size conductors is feeding a certain branch circuit based off of demand, where would I find that in the code book? The table.
Table 9.
Table 9 will give you the circumference of the wire, but it won't tell you the size of the wire. 310-15B16. So if you look in your code book under 310-15B16, you'll find the actual conductors sizes based off of the ampacity or the required load. All right. Also, identify at least 3 situations where ampacity of conductors must be derated. Okay, deration is essentially where we have a situation where we were going to, if typically a 200 amp service would be standard a 4-aught, depending on the situation, we may have to go up in size because that wire is no longer rated for what it was based off of temperature. But let's look at the factors right here. It says no more than 3 current carrying conductors. That means 2 hots and a neutral, okay, and a raceway. Ambient temperature surrounding the conductor exceeds that rated of the conductors. You have a voltage drop, meaning you have an excess in length, how far away it is. and your cable assembly is bundled more than 2 foot in length. So if you got wires that are all bundled together and it exceeds 24 inches, then they're going to be derated based off of the electromagnetic field and the interference between them. So, all right. Branch circuits and load calculations of branch circuits using NEC requirements. So branch circuit conductors between the final breaker and the outlet. Okay. So that is the purpose of the branch circuits and load calculations. So you got your breaker, you got your outlet. Well, what is the demand load on that outlet? And that's going to determine what size wire we run, essentially. So if I know that in this building, office, home, whatever I'm at, if I know for a fact that this circuit's going to run, let's say, an air compressor, and I know air compressors pull approximately 12 to 15 amps of power, depending on the size of the compressor, then I'm probably going to make sure that that's either a 20 or 30 amp breaker. Now, when we're dealing with appliances, we have to do a couple things. One, we have to actually look at the nameplate rating on it, and it's going to tell us what the ampacity of that breaker is. And let's say, for example, it said that breaker must be a no larger than a 25 amp breaker. Okay, if I go with a 25 amp breaker, there's a good chance I need to run a number 10 wire to it. Okay, because I can't use a number 12 wire, even though a 12 wire is, if you go to 310, B15, 16, it's going to tell you that that number 12 gauge wire. So let's look in there, 310, B15, 310, 15, B16, and let's see exactly what is the maximum amperage for that. Let's see right here. So it says right here in the table, 310, 15, B16, that a number 12 gauge wire based off of 90 degrees Celsius, we're going to say it's THHN, is rated up to 30 amps of power. Now, if that's continuous use, you've already derated it now. You've got to derate it to 80% of its maximum size. So what is 80% of 30? You can take a guess. It's going to be about 25. Okay, so about 25 amps of power, which that nameplate rating says the maximum, and that's continuous. So it's kind of like, so I would run a number 10, just because it says right here, number 10, non-continuous use is good up to 40 amps of power. So that's the safer way to go. We have to manage sometimes what's safe and what's affordable. Sometimes it's that balance, and it's what you have to, as an electrician, have to make that determination. Do I do what's safe and within the realm of the National Electric Code, or do I cheap out and push it right to the threshold where there potentially could be problems down the road? And most times it wouldn't be a problem, but there's always that chance that it could be. All right. Applicable NEC standards: 210, 220, 240, 340 or 430, 440. So those are all applicable standards and deals with loads. All right, to determine the maximum load by a single phase branch circuit, you multiply the rating of the breaker by the circuit voltage. So for example, if you have 20 amp, 2 wire, 120 volt circuit, then obviously it's volts times amps equals your volt amps or watts, right? So derating, current carrying capacity of the branch circuit conductors. If you have more than 3, we talked about that, ambient temperature, and so forth. All right, so this is the, still never pulled up yet. All right, so let's do this real quick. Let me, all right, so we're back in. All right, so See if I can maximize this real quick. All right, so what is the maximum continuous load that may be connected to 20 amp, 120 volt circuit? We just determined that based off of the 80%. So that's where that math comes in. So if you have a 20 amp, 120 volt. Now, why is that? Why would we make it to where it only has 80% of the breakers ampacity for the load?
So it doesn't burn up the wire.
Absolutely. You're 100% right on that. So we'll make sure that we are rating our wire to where it's essentially 20% greater than the actual demand of the fuse. Because continuous use means that anything that's continuous to use for 3 hours or more. So that rule hasn't changed. Not real sure why it's doing that. Okay. Let's try this for a second. For some reason, I'm having trouble accessing PowerPoint.
Hey, what was that long number you said again?
Oh, the meeting number is 835-6407-2403. All right. So what is the maximum continuous load? We decided was 16 amps. 20 amps times 0.8, 16 amps. The voltage drop for a 208 volt single phase circuit with a load of 28 amps using a number 8 stranded copper at a circuit length of 160 foot is blank. And we find that by using this formula right here. Voltage drop equals 2 times the length times the resistance times the current. And we divide that by 1,000. So in this situation, we have our voltage drop equals 2 times, what was our length? 160 feet, right? And our resistance, it'd be, now, remember we talked about earlier, chapter 9, table 8. So let's go ahead and look at your book, chapter 9, table 8. Four, 5, 12, table 8, here we go. Conductor properties. And it said it was a number 8 stranded. So you scroll down till you see a number 8. And then you see stranded by looking at quantity, the column where it says 1 and 7.
Mm-hmm.
So 1 is solid, 7 means there's 7 individual conductors making that strand. And then of course you're going to scroll over till you see ohms per foot. What is that number you're right here? 0. What?
0.49.
No, we're not quite there. Look at ohms per 1,000 feet.
0.778.
Exactly. So it's 0.778 as your conductor resistance. And then we're going to multiply that times 28 amps. And then that's going to give us, or divide that by 1,000, that's going to give us 6.97 volts. That is your voltage drop for that circuit. Okay. So the key to it is you have all the information except for the chapter 9 table 8 page. So you have to know the reference if you're looking for the ohms per 1,000 foot. Okay. Because if you look right here, like I said, right where it says ohms per 1,000 foot. What in the world? Oh, that's what. No wonder that kept messing me up. Is that mouse right? Sorry about that. Not sure what that. Now that makes more sense. Understand why that mouse kept doing that. All right, the ampacity of 120 volt single phase load rated at 800 watts or volt amps. So we literally take 800 volt amps and we divide it by what? 120 volts. You got to find amps. 6.67 volts, right? 800 divided by 120 equals 6.67. All right. Let's open up the next section here. And I'm going to post on here as well. I may add it to this last sheet as the actual formula sheet that I want you guys to let's do this real quick. Let me share this right here. All right. All right, so what is the most important piece of information needed when you're sizing your cooking equipment? So if you have a piece of equipment going into your building, residence, whatever, what do we need? What information do we need off of that equipment?
See how much load is pulled.
Absolutely, we need to see what is current. The nameplate rating of the equipment. We need to know what is it saying the maximum wattage or volt amps that piece of equipment is going to be using. So why must the branch circuit supplying the 80-gallon water heater be rated at no less than 125%?
Because it's pulling nonstop.
Right, it's exactly, it's called continuous, right? It's considered to be continuous load. So our lighting load branch circuit calculations, they're based off of what type of lighting, or is it incandescent, electric discharge, LED? What is this circuit voltage, and whether or not the lighting is continuous duty? A load for recessed lighting fixtures is calculated by using the voltage or the maximum volt amp or watts rating of the fixture and the lamps. So when the exact volt amp rating of a load being plugged into the receptacle is not known, a rating of not less than 180 volt amps per outlet is used. So if you don't know what the load of that receptacle is going to be, you just go ahead and anticipate we're going to rate it at 180 volt amps. Period. Because we'll divide 180 by 120. It's 12. So it's essentially 12 amps. So say, okay, if I rate this at 12 amps, no, is that 2 amps? It's 2 amps. 1.2 amps is what it is. So 1.2 amps, then essentially I can put 13 outlets on a 20 amp circuit. So, now you can multiply 13 times 1.2. So that comes out to 13 times 1.2 equals 15.6 amps. So we obviously want to have a balanced load. If we don't know what that's going to pull, we just go ahead and anticipate it's going to pull 1.2 amp, just in general. At least 2 20 amp circuits for the kitchen. Okay, got two circuits. That's to include the pantry, breakfast room, and your dining room receptacles. Feeder load for each circuit computed at 1500 volt amps, and no circuit may serve more than one kitchen. This hasn't changed from before. So whenever you're doing your general lighting load, first thing you're going to do is you're going to multiply your square footage times 3 volt amps, right? The second thing you're going to do is you're going to go ahead and say, I've got 2 kitchen circuits rated at 1500 watts each. So that gives you 3000 volt amps combined. 2 times 1500 equals 3000. And then the third thing you're going to do is you're going to multiply 1 1500 volt amp circuit for your laundry room. So you've got your square footage plus your 3000 plus your 1500. So that puts you 4500 volt amps plus whatever your square footage is. And then you're going to take that first 3000 watts at 100%, and everything after that is going to be multiplied by 35%. Okay, and that's going to give you your general lighting load. Okay. Does that make any sense whatsoever?
Yeah, we did it on the board.
Yeah, we've done it 100 times, right? So we just want to make sure that we're recapping what they're talking about right here. So you got your laundry circuit, essentially saying the exact same thing. Feeder load for each circuit computed at 1500 volt amps. Loads for household electric dryers is calculated at 5,000 watts unless, or the nameplate rating of the dryer, whichever one is larger. Okay. Oh, there it is. It says whichever is larger.
Well, how do you do that if you don't know what the dryer is?
If then you go at 5,000. Because I don't know. I haven't built my house yet. I'm trying to build a load calculation off of a building that's not even built yet, right? Because I have to turn this information into the power company. Because they have to know what size load. They have to know what size transformer we're going to put outside your house based off of what demand you're going to have. What happens if your demand of your house is larger than the transformer that they put out there?
It'll blow the transformer.
It'll blow the transformer. It'll try and use more than it can process. We'll put a strain on your conductors, and then eventually it'll blow that transformer. So think about it. Does the NEC specifically require a dedicated branch circuit for a washing machine? Yes, it does. I know it doesn't say that, but it does. So let's see. Actually, I can. Let's see if it does say it right here. That's not what I wanted. Let's see here. The NEC does not specifically require a separate circuit for the washing machine, but it does require a small appliance circuit in the laundry room, which usually is used for the washing machine. Now, I thought in my mind when I saw that single outlet, does it require a single outlet? And the reason we use a single outlet as shown in here, I'm gonna make this, I'm gonna increase this real quick. Let's see, oh, share again, there we go. All right, the reason being is why do you think we would use a single outlet versus a duplex outlet in the laundry for that one?
Anything else in it?
Absolutely. First of all, first and foremost, if there's a sink in there and you plug in another whatever to it, phone charger, whatever, in that device, or like my wife does, she puts a cordless phone in the laundry room. So if she's in there and the phone rings, but what if it falls in the wash basin while she's hand washing the clothes or something? Yeah, but especially if it's not GFI protected. You can't put a GFI receptacle there because that machine motor will trip the outlet right in the middle of your wash. It'll be a frustrating scenario. So that's why the single outlet. Just keep that in mind. All right. Loads for household cooking appliances are calculated using demand factors listed in NEC table 220, 55. All right. So go ahead and open your your code book, 22055. 22055. It's going to talk about your ranges. And it's going to tell you how many ranges, and if it says this many ranges, then it's going to be rated at this load. So 44, 54, 55. There it is. So if you have one appliance or one range, all right, and if you read up there, it says demand factors and loads for household electric ranges, wall-mounted ovens, counters, mounted cooking units, and other household appliances over 1 3/4 kW rating. Column C is to be used in all cases except and otherwise permitted in note 3. Okay? So, if you have one appliance, it's rated for what? 8 kW. That's what that means. Are you there yet?
You said 220/55, right?
220, table 220. Should have been like on the very next page where you were. Right there. So look all the way in the far right corner. Column, I mean. Far right column. How many appliances? One. Yep, rated at 8,000 watts. Because it says, note the maximum demand is in kW. So say 8,000 watts. All right, the single most important piece of information required to size the circuit equipment is the nameplate rating. If you don't have the appliance already. So we always rate it based off of the nameplate rating or 8,000 volt amps or watts, whichever is larger. All right, which note under NEC table 225 refers to this installation where you actually have a cooktop and an oven separate? So it's 2 appliances.
That's a really old picture.
That's an old picture, right? But it's actually 2 appliances. So we're going to actually rate them at 2, right? So under which note? So look at the notes down below. So if you have, note 1 says over 12 kW through 27 kW, ranges of all same rating. All right, so it's not necessarily note 1. Let's see what note 2 says here. If it's over 8 3/4 kW and through 27 kW ranges of unequal ratings for ranges individually rated more than and of different ratings, but none exceeding 27, on an average, the rating shall be calculated to obtain total calculated loads. The Lewis method, column C, is permissible to add the nameplate rating of all household cooking appliances. Column A. All right, so look at number 4, note number 4 down below that table. It says branch circuit load. It shall be permissible to calculate the branch circuit load for one range in accordance with table 220/55. The branch circuit load for one wall-mounted oven or one center-mounted cooking unit shall be the nameplate rating of the appliance. The branch circuit load for a counter-mounted cooking unit and not more than 2 wall-mounted ovens, all supplied from single branch circuit located in the same room, shall be calculated by adding the nameplate rating of the individual appliances and treating this total as equivalent to one range. So you take the 2 together and you add the current. So the cooktop right there, we're going to say that cooktop's going to pull 15 amps because it's got 4 eyes on it. The oven right there is going to pull, we're going to just go ahead and say 5,000 watts. Okay. So how many did I say for the cooktop? 15 amps. 15 times 120 equals 120 equals 1,800 plus 5,000, 6,800 watts. Okay. So we can count that as 1. So I based off that information right here. So 6,800 or 8,000, which one's greater? So that's one I have to go with. So I'll go ahead and say at 8,000 watts, 8,000 divided by 240. Why 240? I've been saying 120 this whole time. Why all of a sudden am I saying 240? Because that's the voltage. When you're dealing with appliances like ranges, furnaces, stuff like that, water heaters, they run off 240 volts. So that tells me it's 33.3 amps. Okay? So based off of your code book, 310.15b16, continuous use, because that oven could be on for hours. Not that it, well, let's just go 310, 15, B60. All right, now I just said 33.3 amps, right? So I'm going to scroll down till I see 33, which, and we're going to go with copper. It says I could use the number 10 for the 40 because it goes up to 40 amps. But in the industry, we go ahead and run an 8. Just because, like I said a while ago, we could put a 10 there and be within the realm of within code, but we typically, for ranges, we put an 8, 4. Now, why do I run a 4th wire? Why do I need that neutral wire versus, because a lot of times for your like your water heater, you have 2 hots and a ground. That's all you get, no neutral. Why do I need a neutral for my range?
To carry back.
Not necessarily carry back, because I can do that across the ground as well. Not supposed to, but I can. It's because of the electronic devices in there. They require that 120 volts system. Well, for the balance too, definitely balance the loads. But for that particular reason, anytime you have a computer inside of a piece of equipment, it requires a neutral. So that's why a lot of older homes that don't have that 3rd wire in their range, 3rd wire in their dryers, their equipment starts giving them problems a lot sooner than newer homes because they don't have that neutral, the isolated neutral.
My grandfather still has that.
Yeah, there's a lot of people. Oh, them appliances.
Yeah, just like that same picture set up.
I believe it. So we got water heater loads for fixed storage water heaters with storage capacity of 120 gallons or less. Branch circuit to be rated at no less than 125% of the nameplate rating of the water heater. Okay, continuous use, remember, 125%. Considered to be, it's also to be considered continuous use or continuous load. Electric heating loads, for example, up north, we have they have the plug-in heaters for their engines so their engine blocks don't freeze in the middle of wintertime. So branch circuits can supply any fixed size electrical space heating equipment. If 2 or more outlets are supplied, the branch circuit size is limited to a 15, 20, 25, or 30 amp outlet.
And those are everywhere?
They're not everywhere, but they are definitely in certain places. I mean, they're more predominant up north now here. You won't find them here in the south because it doesn't get. It does freeze, but not to the point where we have to worry about it. Just buy a little antifreeze and you'll be okay. So put it on a carport. Outdoor services may be designed to supply both lighting circuits and branch circuits for other loads. This is the nameplate rating for an air conditioner. Now, one thing I want us to look right here on there is it's telling us what our voltage is. It can be 208 to 230. Single phase, 60 hertz of electricity. My compressor run load amps is telling me that it's at a 18.6 and 18.6. 1/3 horsepower. Your maximum fuse, this is key, 40 amp breaker. So what size breaker do you think I'm gonna put on there? 40 amp breaker. It just told me exactly what size breaker to put on there. I don't get a choice in the matter. I don't get to choose. So, I think I'll put 50 amp. Why wouldn't I want to put 50 amp? 50 amp protects it. Let's say I've got a number 8 wire. Number 8 wire is good 55 amps. Why wouldn't I be able to put a absolutely, because what if it surges? It's a motor. If that motor surges beyond its limiting capability, then we'll burn the equipment up before it ever even trips. And that's not what we want. We want to make sure that equipment, the overcurrent protection device does its job before that piece of equipment burns up, and then you have to spend another $7,000 on a new AC unit. All right, so what is the calculated load in amps for a 120 volt circuit supplying 8 recessed fluorescent fixtures operating continuously? Each fluorescent ballast is rated at 0.5 amps. All right, so we're going to say it's 5 amps, and this is why. We have 8 fixtures at 0.5. That gives us 4 amps. 125 percent, which is continuous load, of 4 amps equals 5 amps. It's basic math. It just told us we have 8 lights that draws 0.5 amps. So 0.5 times 8 equals 4. 4 times 125% equals 5. What is the maximum number of continuous duty duplex receptacles that can be connected in a 20 amp, 120 volt circuit in commercial buildings? Duplex receptacles. Remember what we said? 180 volt amps, right? Per outlet. So what is the maximum number of continuous duty duplex receptacles that can be connected to a 20 amp, 120 volt circuit in a commercial building? 10. Continuous duty. We didn't multiply it times 125%. So 20 amps times that equals 2,400. Rating per receptacle is 180 volt amps times 125% equals 225. And we divide that from 2,400, that gives us 10.7. So we'll say 10. Does that make sense? All right, so we just said continuous duty, right? How many watts per outlet? Remember what I said a while ago? 180 watts per outlet. That's per outlet. Because we don't know what's going to be plugged into that outlet. So it's 120 times 1.25. That comes out to, what did that come out to right there? 225. 225 volt amps or watts. All right. So I take that 225 volt amps and I divide that by how many, what did they say a while ago? 2,400. So I got 2,400 volt amps divided by 225 volt amps. That's going to give me 10.7 devices. Round down to 10 devices. Just got to remember, anytime you see that continuous duty, you think 125%. 125%. So what is the total load in volt amps for 4 small appliances in a single family dwelling? Small appliances, each small appliance is rated at 1,500 volt amps. 6,000 volt amps, yep. What is the demand load in amps for one household dryer with a nameplate rating of 4.75 kVA? That is correct. 4.75 times 1,000 equals 4,750, or 5,000 volt amps, whichever is larger. Yep. Nameplate, whichever is larger, right? What's the demand load in amps for two small burner electric range with a nameplate of, for a small 2 burner electric range with a nameplate rating of 7,000 kVA, single phase, 240 volts. What is the load? So we're going to take that 7,000 and divide that by what?
240.
240. 7,000 divided by 240 equals?
29. 30.
Says 23.3. So we take that, multiply it times 0.8, it goes up to 5.6. Yeah. Like I said, we'll have that sheet that'll be able to give you those formulas. But the whole purpose of this is, remember when we talk about appliances, we take out 7,000 volt amps, we multiply it times 0.8 based off of the number of appliances. 80%. All right, what is the ampacity of a water heater with a nameplate rating of 8,400 volt amps at 240 volts? It's continuous use, but that shouldn't make a difference. What is the ampacity of that?
35 amps.
125% continuous load. Yeah. So it's 35 amps times 125%. Water heaters are always 125%, always continuous load. What is the minimum conductor ampacity for 1,200 watt, 240 volt baseboard heaters? Minimum conductors ampacity says 25 amps. So we do 1,200 times 4, 4,800 divided up by 240 equals 20. 20 times 125% equals 25 amps. So if you haven't figured out, we got to do continuous load on almost every one of these. So what size copper branch circuit conductors are required to supply an air conditioning unit with a nameplate of 18 amps, 3-phase? So we do 3-phase. We do the square root of 3, so we multiply it times 1.732. So the number 10 at 125%, and 60 degrees Celsius, 100 column, table 310B 16, 22.5 amps equals number 10. $18 amps times 125% AC. All right. We're almost done here.
And my girlfriend's dad, he does that rewards thing.
Okay. Last section here. All right, commercial applications usually require signs to operate for more than 3 hours at a time. Therefore, the sign circuit is typically considered continuous load. Under this condition, the branch circuit calculation is multiplied by 125%, and the sign load cannot exceed 80% of the branch circuit rating. Okay. Read all that. Yours never did work, did it? So it's saying calculate loads on multi-outlet assemblies, calculate show window loads, sign loads, loads for heavy-duty lamp holder outlets, commercial kitchen equipment loads, and motor loads and welder loads. A surface or flush raceway holding conductors and raceway receptacles. This is considered a multi-outlet assembly. It's assembled in a field or factory. It can be done on the job site or in a factory. Maybe a single outlet wired to one or more circuits, and it's equally spaced at 6 inches, 12 inches, 18 inches, etc. All right, this is considered a 5-foot assembly used in other than residential applications, i.e., normally in commercial settings. We have these actually here at our school.
What is it?
It's an outlet strip. It's a multi-assembly outlet strip. So if we were in the welding lab over there in the classroom, I could show it to you. That's where we used to have them. Show window loads, receptacles are at least 125 volt, single phase, 15 amp or 20 amp outlet per 12 lineal feet of window. Branch circuits shall be 180 watts or volt amps per receptacle, or compute at 200 volt amps per lineal foot of window. Feeder or service loads, total not less than 200 volt amps per lineal foot of window. So in these windows, it says each of these show windows measures 5 feet in length. Based on NEC 220, 14 G2, what is the branch circuit load for each window? Okay, it's typically 180 watts per outlet or 200 per lineal foot. So what is the branch circuit load? So let's go back one. Let me see, because it should be let's see, let's see, previous here. I know I got a way I can actually show these little questions. Overlaid load. Arrow. There we go. This will work. Got it. In this particular one. Says show window loads, calculate 5 foot times 200 volt amps equals 1,000 volt amps at 125%, which will give you 1,250 volt amps. Because remember what I said, it's 200 volt amps per foot, per lineal foot. So if I have a window right there, and that's part of my marketing, whatever, and I've got stuff going on, they calculating per foot is rated at 1,200 watts or 200 watts. So that's where they were going with it. All right. Let's bring this back. All right, sign loads, heavy duty lamp holder outlets, incandescent fluorescent lighting, not to exceed 20 amps. Neon tubing, not to exceed 30 amps. At least 120 amp that supplies no other load, and loads computed at minimum of 1,200 watts. That's your sign circuits. Your heavy load lamp holder outlets are a minimum of 600 volt amps. Commercial kitchen equipment loads. Loads are calculated based on the equipment nameplate rating. 220.56 lists your demand factors. 220.56 applies to cooking equipment, dishwasher, booster heaters, and water heaters and other kitchen equipment. So what would you consider a dishwasher booster heater? Hearing that word, term, or whatever, what does that? What goes? What do you think of when you think of that?
Tankless water.
Tank. Well, it's an instant hot water heater. That water gets super hot, so it has a high demand to it. So just keep that in mind. Use of NEC motor tables require information from motor nameplates to include horsepower, voltage, phase, design letter. To determine branch circuit conductor size, you'll calculate 125 motor full load current from table by 125%. So this is a buck and boost transformer that's actually a mixer. But a buck and boost transformer would actually change the power for some appliances in kitchens. For example, let's say in my kitchen, the only thing that requires a special amount of power is this ginormous mixer. Do I bring in 3-phase, 208 with a stinger leg and all that just to accommodate one appliance? No, I would literally bring in whatever is best And then if I have to change, downgrade, or increase, then I'd use a buck and boost transformer just to supply power to that piece of appliance. Connected to standard 12208 service using buck boost. Will this affect the branch circuit load calculation? Yes. What would happen if a buck and boost transformer was not used? It would draw a tremendous amount of load. It would just, let's see what they say. They're saying that it should not change the circuit calculation as long as it is a motor load using a buck and boost transformer to raise the voltage. It allows the branch circuit current to remain as stated on the motor nameplate instead of that of the higher. Okay, well, that makes sense then. Because the higher the voltage, obviously the lower the amperage. So, blah, 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 240, which is cause it to draw more current than is rated for the windings will be eventually burn out. So it'd have to have it or else it would just burn out. All right, so let's put this back. All right, so welder loads. So if we go to Article 630, branch circuit conductors and overcurrent protection devices are sized using your primary current and the duty cycle of the welder. So this is a transformer welding machine. That's an engine-driven welding machine. So the load for 8 foot of multi-outlet assembly used simultaneously is what? 8 foot of multi-outlet based off of 180 times 125% comes to what? $180 times 125%, 1.25 times 8. Oh, I said simultaneously, so I assumed it meant continuous load. Okay, that was my bad. I just mistook when it said simultaneously. Yeah. That means all the outlets are being used at one time, not that they're being used for over 3 hours. How many receptacles are required for 60 lineal feet of show window area? How many receptacles are required for 60 lineal feet? Remember, you're only required to have one outlet per 12 feet. 12 feet. What is the maximum continuous load in volt amps that may be connected to a 15 amp, 120 volt sine circuit? So they're using the formula of 15 amps times 120 gives 1800. Multiply that times 0.8.
5.8.
Because we say 120 amps or 125% based off of continuous load when it deals with your actual feeder. But when it talks about the actual, how did it say that earlier? It said it right here, and it was very distinctive when I said continuous load is a load where the maximum current is expected to continue for 3 hours or more. And then referred to it earlier, and I meant to foot stomp that. Like, man, that's going to be important to know right here. Calculate, sine loads, multi-outlet assembly. The 0.8 is based off of, let me circle back on that one, but it has to do with your overcurrent, the actual overcurrent of the circuit. I do know that because it actually explained it earlier. So, general purpose. We'll circle back to that. Like I said, it was very distinct when it said it a while ago, and I meant to make mention of that. All right. Per NEC 22014E, outlets for heavy-duty lamp holders are each calculated at a minimum of so okay, heavy-duty lamp holders. Yep, said that earlier. What is the demand load for 4 units of commercial kitchen equipment with a total volt amp rating of 36,000 watts? Four units, 80%, 36,000 times 0.8 equals 28. So when you see the word demand load, multiply it times 0.8. When you see continuous load, it's 125%. What is the full load current for a 5 horsepower 208 single phase motor? Full load current. And we back up. They didn't give that one up. So let's see here. 5 horsepower. So horsepower is actually identified if you go to horsepower. What was that? 5 horsepower. I remember in the code book exactly where we find horsepower. Let me do this real quick. Let's see. That didn't answer anything, did it? Motors, horsepower. I'll circle back to that one, but each horsepower is rated at, gosh, what is it? Yeah, I'll get back on that one. That one's, because I got to figure out exactly what the horsepower is for 6 units, 65%, 4 amps, motor full load for 2 horsepower. So if we look in section 3.6.0 under motor loads, and it says, look in table 430-248 in the code book for single phase motors. 430-248. Table 248, there we go. Single phase, 5 horsepower at 200 volts equals 208, it's 208, yeah, equals 30.8 amps. It's literally in that table. If you look on page 70-321, right there. So there you go. Find 5 horsepower and look at it, 208 volts.
30.8.
Yep, 30. Yep, 30.8. All right, so what size copper branch circuit conductors would be required to supply a non-motor generator arc welder with a nameplate primary current of 100 amps and a duty cycle of 50%. All right. So based on table 300 or 630.1.11a, we're going to say, so go to table 630.
Either times 0.71 times 100.
600.
It's 70 dash
Oh,
519.
yeah. All right. 60 degrees, let's see, column 310 requires a number 3 hog wire. Let's do. Okay. Any questions? Awesome.
It's a lot.
It is a lot. So what I'm going to do here is before I stop this recording is I'm going to go put that sheet and get it out there so that you can review that if need be. So I'm going to pause this real quick. Okay, listed right here is going to be the formula sheet. I know it's kind of tough to see right here, but let me see. I'm going to use a function key here to try and actually increase the size. There we go. So you should be able to drag and carry over to be able to see it from here. But as a video, I don't think you can. No, you don't have that availability. So what I'm going to do is I'm going to actually try and go slow here to where you guys can see. I'm going to give it to you the full screen again. You may have to take a snapshot with your camera or something like that, or do a screenshot on your computer if that's what you're doing.
Yeah, or you can pause the video.
Or you can just pause the video. Yeah, and then use your control and then zoom in like that. So there's a second sheet here as well. So a little tougher to see, but we'll zoom in on that and look here. These are all the different formulas that we went over. Even shows where to find the formulas at. For example, 430/52 talks about the horsepowers, voltage drop, 3-phase, so forth. So this same formula sheet is over in the testing lab. So you have access to this sheet when you do test. So it'll be a good opportunity for you to practice reviewing it though. So I think that's it right here. So hope this helps. Hope this gives you some insight on what 26301 encompasses. I encourage you to do a couple things. Make sure you read the terms because it does you no good to go through this module and not understand what you're reading. And the second thing is do the review questions. Those review questions mirror the actual test. May not be word for word and question for question, but it's going to give you a good idea of what the questions you're going to be asking for. So, all right, well, good luck. Let's go ahead and end this session. Thank you guys so much.